But today I'm going to talk about WebGL because it's something that I really, really care about too. So, no game on today, but a lot of 3D at home. A year ago, when WebGL was rather new, I did a small demo and I showed one of my friends. It was a very simple demo with a time shader, kind of fancy, and my friend loved it. Like, he loved it like a teenage girl outside of our bar. He was like, oh my god, that demo was amazing. I wish that all internet was in 3D. I was like, no, wrong, and fuck you, actually, that's really what I mean. But it raises a question, like, what does 3D on the web actually mean, right? Because you go to a website, like on Google, you do search, and that web view clearly is not in 3D. That's 2D. But if you are really deep in the middle of it, it's already on 3D now. Except it's really easy because, you know, a web view is flat, so it doesn't really have 3 dimensions. So of course, you're going to think, okay, you're going to start that. When we talk about 3D on the web, we mean those parts of the web that are actually rendered by the GPU, by the graphics processor of the machine we're working on. But this is not really true because, as you probably know, all modern web browsers, they have what we call a DOM, and the DOM gets converted into a render tree, and that render tree, the elements of the render tree get grouped together into layers. And those layers, depending on the way the CSS transform affected, they get rendered and deposited on the GPU. So basically, in a modern web browser, if we don't have anything on 3D on the screen, everything is composited and rendered on the GPU, on the graphics processor. So, of course, the question is now, what the fuck are we going to talk about today? Well, we're going to talk specifically about WebGL. WebGL is the JavaScript API to render graphics accessing directly the GPU. That's what WebGL is, but this report, here is what it is not. WebGL is not an API for 3D graphics. You see, WebGL is the building blocks for the GPU, but you don't really need to do 3D with that. You can do 2D graphics with that, and you can make it very efficient that way. But we want to focus on 3D this time. Also, WebGL is not an OpenGL wrapper. You may think that from the name, but it is not. WebGL has an API that looks like OpenGL, but it's not implemented from OpenGL. For instance, OpenGL on Windows sucks. It's terrible. So what Firefox and Chrome do, they use this library called Angle, which what it does is it takes the WebGL calls that look like OpenGL API calls, and they translate them on the file to that directly, which is the API the Windows really works. So from that point of view, WebGL on the Windows doesn't use OpenGL at all. It goes straight into directly. So it feels, you know, like that fairy tale where, you know, there is a wolf and the wolf is the grandmother and he's wearing the clothes of the grandmother, but you can still tell it's a wolf. Then it turns out that the wolf is in fact Steve Ballmer. So something like that. If you ever been on a website with a 3D element on it, you have seen something very interesting, right? There is a 3D element and you can interact with it, right? You can put your mouse and click it and so on and so forth. But besides the 3D element, you can also see that there are other parts of the website that are not 3D. They are plain old HTML on the DOM, like normal HTML on the website. We can see it right now with the Firefox 3D view of the DOM. And we see that there's actually a part that is WebGL and a part that is normal HTML. So what this means is that basically what we do, we have normal HTML on the website, and we have a canvas element, a normal canvas element, and in that canvas element, we produce our 3D graphics using WebGL. That's basically how it works. Of course, since it's a canvas element, we use this classic canvas get-context API, which is the same API we would use if we were trying to do fancy 2D graphics using, you know, your canvas API. But when we do WebGL, we just use get-context with the WebGL argument, and we're going to get a WebGL context if WebGL is available on the machine. That way we can use that context to draw into that specific canvas. This has a huge advantage, which is that since we get context from the canvas, if we have two different canvases in a DOM, we can get the context from one canvas and the context from the other canvas, and when we draw one canvas, it's isolated to that canvas, and when we draw the other, it happens on the other. This is very convenient because if you have ever tried to do a desktop application in 3D and you try to mix two OpenGL rendering contexts, that's basically a nightmare. That's a living hell. But JavaScript makes this very, very straightforward. So that's a nice thing to have here. that is the perfect moment to render, and it gives us all these advantages. For instance, if we're in a desktop client and we switch tabs, the web browser will stop requesting animation frames and we will stop rendering. If we are on a mobile phone, the web browser can choose to request animation frames less often to save battery, for instance. And if you come from a desktop background, you're probably thinking, what about double buffering? And if you don't think that, well, I'm not spending any ways. Double buffering is the thing that happens on desktop applications when we use 3D, which is And in order to turn it from its local space into the world space for the mesh, what we do is multiply by matrices. What we call the model matrix that goes into world space, then we multiply again by the new matrix that goes into canvas space, and we multiply again by the projection matrix that goes into screen space. This is the core concept behind actual 3D graphics. We got vertices that are stored in arrays, vectors of 3 elements, and we multiply those by matrices to get a final position in the world. Now, this matrix multiplication we could do it with JavaScript code, with a lot of JavaScript code, but this is not a very efficient thing to do, because if we want to show like 2 million vertices on the screen, we need to multiply every single one of those 2 million vertices by the same matrix to find a final position on the screen. So we're not going to do that. We're going to do something different that's called shaders. That's how we actually multiply things. A shader is a program that runs on the GPU. You can tell it it's called a classic shit. This is a very good way to describe it, pretty straightforward, but it raises many more questions. If a shader is a program that runs on the GPU, or the graphic processor, then what language is it written in? Well, I give you a clue. The language starts with an N. It's called not JavaScript. Actually, it's called GLSL, the Open GL Shader language, and it looks something like this. And you may be thinking, okay, very funny, this kind of looks like JavaScript. So, yeah, it kind of looks like JavaScript. It's like a bastard child between C and JavaScript, so it's not like influencing from both languages. And the point of it is that we're going to need these programs in GLSL to actually render stuff into script. So the question is now, how do we get those programs into the GPU from JavaScript? Well, it's pretty straightforward. We put the programs on a string. We just put them on the JavaScript string and we send them to the GPU. Which makes for programming a sheet, which if you have a JavaScript program and you have like 10 lines of shaders, then that's as big as the string in the middle of the program. So one thing we do very often is use the magic of HTML and actually stick the string on the DOM. Just use the script tag, HTML script tag, and you put that piece of shader into the DOM. And then you can use, whatever your favorite JavaScript API is, like the domain ID, to access the script tag and, get inner text to actually get the content of the shader into the string. And you can actually send the string into JavaScript. Once we have the string of the program in JavaScript, we need to do a very complex and boring process that I'm not going to show the code for, but it basically feels like compiling a C program if we ever have. If we have different shaders for our WebGL application, we want to build every single one of them into native JavaScript objects, and those JavaScript objects then get linked using JavaScript API and get sent to the actual GPU. Well, that's what they're going to actually run. So this is all done through a very, very ugly WebGL API that I'm not going to show because it's basically disastrous. But it's a very basic process. It basically means taking the GLSL string and just passing that to a function that will compile object you can send to the GPU. It's very straightforward. And once we have the JavaScript object that represents our shader, we can actually start doing the rendering. We can start signing it. The concept of the rendering is very straightforward. We have our model view and perspective matrices, and we actually collect lots of our vertices for our mesh. So we just throw everything into the GPU, and the vertices and the shader is going to run there and multiply them and give us the final position on the screen. This is what a very simple GLSL program looks like. Kind of JavaScript. It has a main entry point, like a C program, which is called main, and this is the only thing that is going to run. It is the entry point for this program. And of course, like all programs has inputs and outputs. The main output is the GL position variable, which is the way we're going to, the result of that variable is the actual value We have a list of vertices that usually you never do this by hand. You actually use a helper function that actually throws every single vertex. And then you send those vertices to the GPU the same way you send a matrix. And that's going to get stored inside the shader. Passing the vertices is straightforward too. You need to first create a buffer on JavaScript, and then you're going to bind that buffer to the actual JavaScript array that is going to use those vertices. It's a very, very open API because it comes straight from C, from OpenGL and C, but it's the way they design it, so it's what you have to do. Once you have that, you can actually do the rendering using any of the drop models. We're going to use draw arrays here, and it's pretty straightforward. We actually set the shader up with the matrices we want, and we got a list of vertices. So we call draw arrays, and WebGL is going to take care of everything. It's going to start throwing every single vertex from JavaScript into the shader, and then it's going to return the vertex on the final position. We throw in vectors, we get back a vertex to the final position that's going to be on the screen. Pretty straightforward. But the question now is, there is this point we have to touch here, which is that we have been moving vertices in a virtual space, and we've been projecting them into a point where we can actually put them on the screen. But that's not really on the screen, because we have these vertices with floating point values on a 3D world, in the landscape. And the screen, has this thing called pixels. And we need to go from those 3D vector coordinates into actual pixels. And to do this, we're going to use the rasterization process, which luckily for us, WebGL takes care for us automatically. The point is that WebGL is going to take every single vertex in the final position, and then it's going to find out the actual meshes that they make and fill those with actual pixels, what we call fragments. So we go from having abstract things on the memory of the GPU, abstract positions of a 3D world, into actual pixels that get shown on the screen. These are the actual pixels that will be shown on the screen, or in our case, the actual cameras element on the website. And this is a fantastic thing, because right now, graphic processors are so advanced that we can actually do something we call primary shaders, which means it's a shader like the one we use for vertices, but instead of being called once for every single vertex on the screen, they're going to be called once for every single pixel on the screen, which lets us do all kinds of crazy shit, some very, very basic stuff. Okay, this is what a primary shader looks like. It has an output, which is the color of the pixel. That's everything that the primary shader calculates, the color of that pixel, which is an incredibly powerful tool because when we have this final model and we project it into the actual parameters on the screen, we can choose for every single pixel on the screen what color is going to be. This lets us do things very basic, like actually setting the color for each pixel on the screen, but also one advantage like the texture. We can load the image from JavaScript and actually set each pixel to the color of the image to have a better actual texture. We can do lighting. We can decide how dark or how light is going to be every single pixel on the screen. We can do specularity. We can actually consider the pixels around the pixel and see if they should be shiny or if they should be reflecting the things around them. We can even do advanced stuff like normal mapping, which is faking depth in that flat mesh by changing lighting. It's super cool stuff. And so on and so forth. Vertex shaders, primary shaders are the most advanced thing you can do in OpenGL, and also the cool thing. But the point is, this is a basic overview of the whole process, back from the start. Every single time we need to render to the screen, we need to go through this whole process. We just clear the canvas element, we load our perspective matrices into a shader, and then we start this loop where we, for every single mesh we need to draw, we load the matrices for this mesh and render the object. Then we remove the matrices and load new matrices with the position for the object, and keep going until every single object has been rendered to the screen. And after half an hour, you got a cube in the screen. It wouldn't even be called, it would be a black and white cube, which is a disaster. It makes this for a very, very harsh and uninteresting way to actually do graphics on the web. Because if you actually want to have something fancy, you just use CSS transformation with JavaScript and have something running in 10 lines that would be much more straightforward. Here's the good news though. There is this library called Threedee, which is amazing. It's my favorite JavaScript library by far. It's within my research loops, and it abstracts all of these. It abstracts everything away. All these matrix operations, all this ugly shader code, it just hides everything behind a very, very straightforward API. And in fact, it abstracts so much that if you try to use Threedee on a computer that doesn't have WebGL, WebGL wasn't quite ready. But we're going to go into the web now, we're going to talk about 3D. We need to keep this in mind. We need to try very hard to keep a sense of taste when we bring up into the web. Because it's very easy to just write a WebGL, which is spinning to transition warrior websites. But that's awful. It's very easy to go with your flag and have spinning transition for every single one of the flags. But that's cheap, it's bad. And we need to try very hard because the hardest part about 3D is not actually understanding everything, but using it with taste. Using 3D when it actually needs to be used, when it adds something to the web website. When it's actually a tool for expressing information, not a simple gimmick, a simple flashy stuff that keeps our users busy. It's a lot of work, but we found very similar. We can do some incredibly amazing stuff in WebGL that works on the web, and it's extremely useful. It's the right way to do 3D, but it's the right way because it's made by people who actually understand how 3D is supposed to be used. And people understand that there is a reason why newspapers are flat, which is that most of the time 3D is not the right way to display information. And if you want to display information using 3D, you need to keep in mind everything that's going to happen when users are very interactive with it. You need to keep in mind that maybe it's not the right way to use 3D. Of course, if you're using a game, you're going to do that in 3D, go ahead and do it. But if you're actually going to try to display information, to do something real on a website with WebGL, you need to strongly consider what the implications of this are. But it's going to be available and where it's the right tool for the right job. And of course, we're going to keep working on this. WebGL on the web is very new, but it's coming forward very fast. I don't know if you saw last week, Windows 1.8 came out with the re-release, and it got to Internet Explorer 11, which actually has very nice support for WebGL. It's a surprisingly decent implementation of WebGL. And that means that WebGL on the desktop right now is basically everywhere. Likewise for Android, that already supports WebGL. And iOS, I don't know if it's coming, but it should be coming soon. So the time of 3D is coming soon. We need to be ready for it, and we need to keep taste in mind very much. Because at the end of the day, I don't know what gets you excited these days. I don't know if it's a new JavaScript framework, if it's immutable data structure in JavaScript, or a test suite, I don't know. But I'm pretty sure, as far as I'm concerned, that the coolest shit that you can do with a computer is basically this spine cube. Thank you.
There is another project now, spainjs. Did you know it? Spainjs. It's a different approach. It's just controlling all the rendering from JavaScript. And I think that it's worth for everyone to check it out because it's another. Yeah, but they are building all the stuff from the ground.
The team was taken out because there is still a lot of limitations when it comes to WebGL, especially the last when it runs. But at the end of the day, if you're trying to do something fancy on WebGL, the point remains that no matter how fast V8 or your JavaScript engine is, you cannot do those configurations by hand. I mean, GLSL is periodic and it's a fucking pain in the ass to use. But this is not the way to actually have this kind of fast operation from the web browser in a way that you can display complex graphics. So of course, any language that do everything from JavaScript, apart from being very hard and very amazing, I want to say that, but they also have this performance penalty that V8 or the JavaScript engine use a tracer, which is you take a pixel on the canvas and you draw a parallel line from the camera position, and you can hit something in the 3D world through the collision and find out where you click from your JavaScript callback what's going to be the actual position of the 3D world. So you, of course, you can use every single callback that event that Canvas offers, but you need to translate those resources, the web represents, on top of the canvas to the actual positions on the 3D world, which is a very complex issue. Everything about this is complex, you know, everything is complex.
I have a question about transparency.
Yes.
It's something that with the original OpenGL was very hard to do. It actually sort surfaces if you wanted to render them transparent. But seeing how there is an implementation for their text or index, does that work? Or is it just not implemented and not available in the process yet? If you know.
Can you ask again? I didn't get.
Transparent surfaces and overlaying transparency.
Oh, overlaying stuff over there.
Does that work?
It definitely works, but as soon as you start doing automating stuff, you get very tricky. Because the point is, you saw the flow matrix position stuff. The last step when we actually do the camera projection, the screen projection, is when we flatten everything on the depth, we flatten it into a single coordinate system. And if you want to do transparency, you need to do special kind of screen projection that's going to give us more difference between the different layers, the different layers of vertices. So you actually have a layer approach. And then you need to actually use the primary shaders to set the way that each pixel is set. So you can do transparency, but it's not the same thing you would use in CSS, which is just set the transparency property to 50%. It's got nothing to do with that. You need to go into the primary shader, and there's going to be a point where the primary shader goes for this pixel. And from the primary shader, you need to push back and see every single pixel behind that one, and choose which ones are going to be transparent and which ones are going to be too far back to be shown at all. So, again, everything in WebCam is complicated, but it's so rewarding and so cool that if you want to try it out, it's hard. Any more questions?
I tried to learn more about shaders and stuff like that, and I've always had a problem finding the shader that I want. I know what fact I want. I know exactly what kind of image I want. And provide some documentation books that we can start with shaders on.
Finding the right offering shader is a complex topic because when it comes to vertex shaders, it's very straightforward. You want a very straightforward vertex shader because it's going to actually project the pixels on the screen. But of course, if you want to do something like which is so better today with the lots of particles, you can actually use the vertex shader instead of projecting stuff. You can actually make it move the particles. So from that point of view, the best way to learn how to write shaders and do what they want to do is to learn a lot of C. Because at the end of the day, it's basically a variant of C. So I will start by learning a painful amount of C, and then there is a lot of very good books on actual shaders. One of my favorite ones is Game Programming Course. There's actually 3 editions of it. Game Programming Course 1, 2, and 3. And you can see something of the craziest as shit. It's kind of amazing. You can use vertical shaders to do anything you want. From particle systems to right versus deformation to actual fluid too much software, then you draw it on canvas or by hand. So again, 2D on WebGL is still 3D, so Threedee works very well, and there's a lot of plugins that do it super well. And of course, if you want pure 2D, there is this thing called Michelangelo,